Okay, let's start chapter 3, maybe section 29, and look at the exponential function. Okay, we've defined the exponential function, stated some properties of it. I think we differentiated it. We probably observed that it's periodic in the complex realm. In section 2.14, we define the exponential function, e to the z. There we go. E to the z equals e to the x plus iy is e to the x times e to the iy. Euler's formula would tell us that that's e to the x cosine y plus I sine y. These trig functions tell you we're dealing with a periodic function, periodic in y. So let's establish a couple of little properties here. The first one, lemma 3.29.a. For any two complex numbers, z1 and z2, we have that e to the z1 times e to the z2 equals e to the z1 plus z2 at exponents, a familiar property from the real setting. Corollary to that will be corollary 3.29.a. Any two complex numbers z1 and z2 imply e to the z1 divided by e to the z2 equals e to the z1 minus z2. Or also that 1 over e to the z, that is the multiplicative inverse of e to the z, is e to the negative z. So let's go to the Beamer files and go through the proofs of those two because they're really not too involved. Okay, so when multiplying, add exponents. The corollary was when dividing, subtract exponents. Follows easily, really, from just the definition of the exponential function. Let's take these two complex numbers, z1 and z2, would be the obvious thing in terms of real and imaginary parts. z1 equals x1 plus iy1, and similarly for z sub 2. Now, if we'll take the product, e to the z1, e to the z2, well, we've got the definition of the exponential in terms of real and imaginary parts. So I'll write that out. We're sort of isolating real and imaginary in a sense in this. We'll do our FOIL thing and distribute and so forth. And that gives us the expression as given here. Now, cosine y1, cosine y2 minus sine y1, sine y2, rings a bell. It's a, it's a difference formula or summation formula. It's a summation formula for cosine function. And down here with the imaginary part, we've got a sine y1, cosine y2 plus cosine y1, sine y2 is a summation formula for the sine function. So anyhow, I stated those summation formulas right here because I don't always remember those myself. But sure enough, this piece down here corresponds to, with the negative corresponds to the cosine of y1 plus y2. Here with the sine cosine plus, sine cosine plus corresponds to the sine of y1 plus y2. So the bulk of the work is really done by trigonometry. And we get the e to the x1 plus x2 is common to these. We can factor that out. That leaves us with a cosine y1 plus y2 plus I sine y1 plus y2. This we can express now using the definition of exponential function again. This gives us e to the x1 plus x2 plus I y1 plus y2 using Euler's formula on this part. And that is exactly e to the z1 plus e to the z2. So proof straightforward. It's really just trig and Euler's formula and the definition of exponentiation. The corollary, maybe I should elaborate some on this, basically says when you divide, subtract in terms of exponents with the exponential function. And one little comment about this piece. It says 1 over e to the z equals e to the z to the negative 1. Or more appropriately, it reads 1 over e to the z is the multiplicative inverse of e to the z. And we don't have to prove this. This is actually just notation. This is what multiplicative inverse means. It's really the this notation of 1 divided by is alternate notation for multiplicative inverse. But what we need to establish is that the multiplicative inverse of e to the z is e to the negative z. Okay, so to establish the first, when we've got the division here, we subtract exponents. Notice that if we'll take e to the z1 minus z2 and multiply it by e to the z2, the previous lemma applies to that. So we'll add those exponents, and of course the negative z2 and z2 cancel, giving us e to the z1. Now we've got the product here equals e to the z1. We'll divide both sides by e to the z2, and that produces the quotient equal to this quantity here, e to the z1 minus z2, following that little protocol because we're using what we know. And what we know is lemma 3.29.8. E to the 0 equals 1. That's just the meaning of having an exponent of 0, provided the base isn't 0. So if we want to look at 1 divided by e to the z, that would be e to the 0 divided by e to the z. We've established now this piece of the claim, so we can write that as e to the 0 minus 1 equals e to the negative z. That equals e to the z inverse. That's just notation for the inverses, establishing the second part. So back to the notes. Okay, when we took derivatives, I guess it was back in section 22, we observed that the derivative of the exponential function is itself, and the derivative of e to the z is e to the z. So e to the z is an entire function, analytic, that is differentiable for us in the entire complex plane. If we look at the modulus of e to the z, that'd be the modulus of e to the x plus iy, where z equals x plus iy. That would be, by the observation above, we can write that as e to the x, by the definition. We can write that as the modulus of e to the x times the modulus of e to the iy. We've been through this many times. I think it's an exercise somewhere in our past as well. E to the iy has modulus 1, so we're just left with the modulus of e to the x, since it's real if you like the absolute value, but hey, e to the x is never negative, nor is it 0 in the real setting, so we don't need the absolute values on that part. So we see the modulus of e to the z equals e to the x, so e to the z is never 0 because e to the x, using properties of the real exponential function, e to the x is never 0. So e to the z is non-zero for all complex numbers. In terms of arguments, notice we're dealing with a lowercase a argument. The argument, lowercase a argument of e to the z, lowercase a argument of e to the x plus iy is simply the y, but lowercase a argument, of course, we get all those multiples of 2 pi. Remember, we're treating the lowercase a argument as your choice. The right choice is we're treating it as a set valued function. Brown and Churchill treat it as a multiple valued function. And we've been through this. You know what a multiple valued function is? It ain't a function. Functions take on single values. You let those values be sets and that would clean this up, but that's not how Brown and Churchill do it. So I don't like it, but that's the notation used by the book. We can observe then the surprising fact, and we've done this before as well, that the exponential function e to the z, it's periodic, and it has period 2 pi I. Now that's bad news when we start to look for an inverse of an exponential function. The inverse of an exponential function, of course, will be a log function. So when we try to define logarithm of z, this periodic nature of the exponential function is going to come back to bug us. And you know who's to blame for all of this. It's polar coordinates. It's all this stuff with the 2 pi I that keeps popping up in these arguments. It's the argument's fault that we're having this periodic nature and that we're going to have a challenge in defining the log function. Note 3.29.a states, if we take any non-zero complex number, if we'll put into the exponential function the natural log of the modulus of that complex number z plus I lowercase argument z, then we'll get z back out. So the exponential function will produce any complex number z if you put in an appropriate input telling you the exponential function is on to. So the exponential function takes on all values in the complex plane, well, except for 0, we eliminated that above. So the range of the exponential function is the whole complex plane except for 0. And we'll see this type of thing again when we try to define logarithms. And you might take a little bit of a pause, anxiety or anger over the fact that what we've plugged in here is a number of exponents because they've used the lowercase a. So we're getting that 2 pi I stuff playing a role right there in the fact that they've taken lowercase arg. To illustrate exponentials, find all z equals x plus iy, such that e to the z equals 1 plus I. Okay, let's get back in frame, the little formula at the top, because that's what's going to make this work. We need to get this z value out, we need to input the log of the modulus. Okay, so we'll take the modulus of this 1 plus I parameter. Modulus of 1.1 plus I is just the square root of 2. Argument, lowercase a argument, which we do need because it says find all z, satisfying that condition. Lowercase a argument of 1 plus I, 1 plus I, it's in the first quadrant. It has a reference angle, to use the trig terminology, of pi over 4. That's the principal value of the argument, to use our terminology. And then, of course, we can add the multiples of 2 pi to that. So we get lowercase a argument to be the set pi fourths plus 2 in pi. N can be any integer. And then if we'll then take that exponent to be the natural log of the modulus, so natural log of square root of 2, plus this set lowercase a arg times I, the I is written on the right-hand side. And in so doing, the n has to range over the integers. Then any complex number, and these are the only ones, of this form, where n is an integer, will produce in the exponential function the value 1 plus I. And that's how exponentials behave, in part, in the complex setting. On to the next section.